Hi, everybody. Welcome to the University of Washington Robotics Colloquium. My name is Dieter Fox, and it's my really great pleasure to introduce today's speaker, Rob Platt. He's from Northeastern University in Boston. Rob is working on robot manipulation in populated environments, manipulating objects alongside humans, which is, of course, very well connected to a lot of the work that's going on at the UW as well in the different robotics groups. I'm a big fan of his work because he's really looking at it from all different aspects. So there is learning, there's control, there's planning, and also perception. And Rob is one of the really worldwide leading researchers in this area. He has a lot of experience with some really cool robots. So he was a technical lead at NASA Johnson Space Center, where he worked with was technical lead at the Robonaut 2 project. I think he then also worked with the Valkyrie robot and was involved in the DARPA Robotics Challenge. So he has, again, a lot of experience with these kind of robots that are not just a manipulator, but really fully integrated large-scale systems that also include manipulation and possibly humanoid walking. He also, what I like is recent, for example, his work where he's combining, let's say, model-based insights with deep learning. I think one of the key techniques when it comes to grasping unknown objects is his work on the GPD, where he trains deep networks to generate grasp poses for unknown objects directly from the observations, rather using a model-based approach. And that's, of course, work that's also related to some work that's going on here. And I really like his approaches there. So with that, without further ado, I'll hand over to Rob and look forward to your presentation.
Cool, thank you very much. So Dieter, that is very high praise. Thank you so much for, I'm not sure I think of myself in such lofty terms, but that's great, thank you.
All true.
Yeah, and I think that GraspNet is I think GraspNet is doing pretty well. So I think, yeah, but you need to release the source code.
No, it is released.
Really? Okay, great. So my name is Rob Platt. I'm at Northeastern, and you can see the title, Policy Learning and Spatial Action Spaces. So, you know, several years ago when we all found out about deep learning, I was struck by this almost uncontrollable urge to use deep reinforcement learning to solve all of my robotics problems. So I tried to do this. And the basic model is what you see here at the bottom of the screen. So your robot has a camera on it, and it gets some images, and and there's this big neural network, and we somehow learn a policy that produces motor torque actions at the end. So it's like, you know, in principle, this thing could learn to solve any problem, and reinforcement learning in principle can solve any problem. So this is what I got really excited about trying to do 4 years ago. Now, as most of you have probably experienced, when you get down to actually doing this stuff, you end up running the standard algorithms, PPO, whatnot, on these OpenAI gym environments like what you see down here. And PPO learns to solve these environments, but these are pretty simple problems that are getting solved here. So we're learning to push blocks, we're learning to grasp, we're learning to stack something, maybe we're learning to manipulate something in our hands. But the thing that I was trying to do was, like, there's a picture of Robonaut here on the left. He was trying to solve end-to-end tasks, and it feels like those aren't the problems that the reinforcement learning people are trying to solve. So it seems like there's a disconnect between what we'd like to achieve with robotics and at least what we're doing, what PPO or whatnot seems to be able to achieve. So Yeah, so this talk is about the attempts of myself and the folks in my lab to try to bridge that gap. So, uh, and I guess part of the insight here, the theme here, is that you're asking an awful lot of your control policy. So that's that's embedded in this neural network down here, this convolutional neural network. You're asking an awful lot of this policy when you try to when it has to produce a bunch of motor torques based on some RGB images. You have to learn a very complex policy. And the hypothesis for this talk is that when people are presented with this mismatch here, I think folks in the field react in one of three ways. On the one hand, when they see, we seem to be solving simple problems using reinforcement learning. On the one hand, I think people say that reinforcement learning isn't the way to go. We can use some perception algorithms, but we need to stick with the old algorithms if we want to actually do anything useful in robotics. That's one group of folks in the community, I think. Another group of folks in the community say to themselves, reinforcement learning is really cool. It's just not scaling up to the problem we want to solve. So the answer is we need to develop better reinforcement learning algorithms. And obviously, there's a whole bunch of folks working on that. But the third thing to point out, and this is kind of where I end up, is that we're not applying the policy learning technology that we do have in the most effective way to solve the problems, and that relates to this this significant gap. And we're asking an awful lot of this policy that is trying to be learned here. So hypothesis: we're not learning, doing, or planning at the right level of abstraction. So our approach in this talk, instead of going from RGB images to motor torques, we're going to formulate the problem in terms of a different action space. So the robot is still going to look at images of the world, but instead of commanding motor torques, we're going to command target hand positions and orientations that will serve as a target for a collision-free motion planner. So to be specific about that, we're going to do policy learning, where the actions are the XYZ roll pitch coordinates of a collision-free motion that the robot is going to perform. So your reinforcement learning agent, or whatever it is, it looks at the world, and it essentially tells you what pose, what position and orientation to move the arm to, and then there's some other actions as well. So I think that's I think that's good. So first of all, you should probably recognize that this is this is obviously a 6-dimensional action space. It's a complex action space, and there's a number of challenges that result from working in this action space, and this talk is an attempt to try to overcome those, and we'll talk about that. But there's a lot of benefits to be had by virtue of formulating policy learning problem this way, as opposed to the more traditional pixels to torques scenario. So probably, just think about what the policy has to encode in order to learn a policy that constructs the block structure that you see here on the right side of the screen. So the formulation with these end-to-end motion actions, there's 6 blocks here that have to be placed. Each one of our actions can either perform a pick action or a place action or some other kind of arm motion action. So in the best case, our action space can enable the policy to successfully build this structure in as few as 12 actions, one pick and place for each block that has to get placed there. And that's in a very different place that's very different from what the pixels to torque scenario would do. Pixel torch basically couldn't learn a policy that's going to be able to assemble this this thing. But if we just do something simple like changing the action expression, the action space, then we can. So yeah, so that's and of course, question I'm going to spend the rest of the talk talking about is how to efficiently learn in the so-called spatial action space. So the term spatial action space refers to the action space where actions correspond to a bunch of pose coordinates like this. So it's a problem, basically, makes sense to everyone. This is what we're trying to accomplish here. You can just type into the chat window if you want me to clarify something or you have a question. Okay. All right, great. Pretty straightforward then. Great. So how do we efficiently learn these in these action spaces? So this is actually a bit of a challenge. So the off-the-shelf algorithms don't seem to extend very well, as we'll see in a little bit. I'm going to talk in this talk. I'm going to cover these four ideas that some of them developed by us, some of them not. But they're all pretty important to being able to do stuff in to learn manipulation policies in a spatial action space. I'm going to be benchmarking my algorithms, our algorithms, in terms of using these block construction tasks. And that's not because I think that block construction tasks are the be-all and end-all of manipulation. It's just because it's a convenient thing to benchmark against. So there's a bunch of different structures which, for most of this talk, our policies are going to learn to construct. I just want to point out, block construction, it's kind of challenging for many ways. I mean, the objects aren't very complicated, but remember, we're learning a policy that takes an image as input and it produces robot motions as output. And it could be any robot motion. This policy needs to be able to grasp objects. It needs to be able to place objects stably. It needs to reason about the structural stability of this structure. It can't just place these things in any old way. They're going to fall over. And it has to produce the desired structure that answers some sort of specifications. So achieving high success rates is actually so much challenging. Okay, so great. So now I'm going to start iterating through the list of four ideas that I think are important here. So first is the idea of using a fully convolutional Q function in order to solve simple problems in spatial action spaces. So in order to frame this, I'm going to just, everyone's probably already familiar with deep Q learning, but I'll just say it anyway. So in deep Q learning, we've got a neural network here, which encodes the Q function. And it takes as input an image, which is taken to contain state information. And the Q network, the job of the Q network is to estimate the values of taking various actions that are available to the agent from this particular state in this particular image. So applied to so in the Q network, the critic and the Q network and DQN, there's one output node per action. So extending this to the spatial action space setting, there's a very simple thing you can do to do a basic version of spatial action spaces, and that is to learn to use a fully convolutional network to learn what is often called a Q map. So the idea here is that, again, we've got a neural network. We use a UNet, but it can be any fully convolutional network. A fully convolutional neural network is a neural network that takes an image as input, and it produces as output a feature map with the same resolution, nearly the same resolution as the input image. Okay, so this fully convolutional Q function here it takes as input, we use depth images. It could be RGB, but we're using depth, okay? This thing on the left here is a depth image. It's a depth image taken from an overhead camera looking down at the scene you see here on the left. And of course, there's this half-built structure there. So the Q network looks at this scene, and it needs to make predictions or make estimates of the Q values of all of the different actions which are available to the agent. Now, imagine in this case, now I introduced spatial action spaces saying that the actions were X, Y, Z, roll, pitch, yaw. Imagine in this case that the actions are just X, Y. Okay, so our agent, our agent has the ability to choose any pair of X, Y coordinates and send those to send those as an action, and then the robot will execute a collision-free motion to those X, Y coordinates, and then it'll like control the depth. It'll just move down to the table until it thinks it's close. There's some heuristic mechanism for doing that. Okay. Great. So that's basically what's going on here. So on the right is an example of a Q map, which is produced by this Q network, which is telling you the values of all of these of the value of moving to any pair of X, Y coordinates, and you see that so every pixel in this not to beat a dead horse here, but every pixel in this output map corresponds to one XY position you could be moving to in the input image. Okay, that's the key. That's the key insight. So notice that there's a peak in this output Q map, which is in yellow here with the arrow pointing to it, which roughly corresponds to the position which is located above the block here. So what this is telling you is that this Q network is telling the system to move the hand over this block, presumably in order to, and it's going to reach, it's going to move to that block, and then there's going to be something that closes the fingers. I'm not telling you how to close the fingers, but that part's pretty simple. It's going to move to that block, and it's going to close the fingers, and that's the next step in the policy, which is encoded in the internals of this this deep Q network. So yeah, so this method is actually, so first, we didn't invent this idea of using a fully convolutional network in this way, but it's pretty effective. And one of the reasons it's effective is that the fully convolutional network, convolutional layers in general are equivariant to translations in the sense that if you translate the input image, the structure, which is kind of hard-coded into a convolutional layer, will, if you translate the input, the output kind of gets automatically translated. So that kind of symmetry is kind of built into the network. And it means that this thing can learn spatial manipulation tasks more quickly than would be the case like with a fully connected layer or something. So anyhow, this is pretty cool. So using this method, we can use regular old Q learning or something similar to that to learn to solve this problem that you're seeing there on the left of stacking these 4 blocks in a row. So that's cool. What's missing here? So this was circa a few years ago. Well, we can't rotate the hand, so it's just X, Y, first of all. And we're only handling simple shapes. So in the next section, I'm going to try to overcome those shortcomings. Everything makes sense so far? Questions?
So when you do the Q learning, first of all, I assume, of course, it's a single structure you're learning to build, but do you give the reward just at the very end when it's done, or do you give intermediate rewards for training?
No, in this case, it would be sparse reward. So yeah, so sparse reward on either a cost to go reward or a reward on completion.
Thank you.
Okay, so the problem the thing we looked at just now was great, but you notice that those blocks couldn't change orientation. So a little bit of a shortcoming there. So now we're going to try to correct that. So a very simple way to correct that which has been used by folks a lot, is it's the same approach, except that instead of producing one Q map, you produce a bunch of Q maps. You know, each one is on a different channel, and each channel corresponds to some preordained orientation of the manipulator. So, you know, you imagine like your hand might be in like 16 different orientations. You learn a Q map for all 16 orientations, and you do that. So that can work. It's not great. There's a lot of, you know, it's not the most efficient way to learn. We're going to try to do better. And we're, you know, we also need SE3, not SE2. Okay, so the key idea here is what's known as an augmented state representation. So this is a little known approach to handling high dimensional action spaces. So most of the time when people get a high dimensional action space, they whip out DDPG or PPO or something. And these methods work by having an actor network that produces a multi-dimensional output that and that gives you this that enables you to specify actions in a large action space. It turns out that those methods just don't work very well for the problems that we're looking at, and we'll see an experiment that shows that in a little bit. This is an alternative approach. So the problem we're trying to solve is to learn policies over high-dimensional, complex action spaces. Okay, so imagine that we're given this MDP shown here, where you have states, and you get to take actions that have three components. You know, X, Y is the first component, theta is the second component, and Z is the third component. And you select an action, a fully specified action, and then, you know, your gripper moves to that pose or something, and you arrive in the next state. Okay. In the augmented state representation approach, we reformulate the MDP in such a way that we can select each of these action dimensions sequentially. So that's shown here. So instead of selecting all three components of action at once, we're going to select action 1, and we're going to transition. We're going to select action 2, and then we'll transition again. We'll select action 3, and I'll transition again. This is still an MDP, but now we have an MDP that's been augmented with additional states. What are the additional states? It's that state and that state. So this state here, this first state, is the state of having been in underlying state S and having taken action 1. So this state, this augmented state, essentially remembers that the agent has just taken action 1, that it moved to some XY coordinate or something. Now, once you're in this particular augmented state, the action space is constrained. You know, this is like the formulation of the MDP. The action space is constrained, so you can only select like an A2 action, or in this case, a theta action. And likewise, and then you transition to a state that remembers the next action you took, and now you have the option of executing an A3 action, which is a Z action, and then you transition to the next state. So this is an idea that has been around for about 10 years, maybe a little bit longer. It's kind of cool because it is especially relevant for deep reinforcement learning. Deep reinforcement learning is really, really good at handling large state spaces and you know, large complex state spaces and generalizing over these large complex state spaces. It's not very good at reasoning about large action spaces, because the action spaces are like, they're on the output of the network. And it's not to say that we can't design neural networks that can do a better job generalizing in action appropriate ways, but it's just like, you know, handling large state spaces just comes right out of the box with deep learning, and it's just a little more challenging with large or high dimensional action spaces. So what we're doing here, obviously, is we're buying ourselves, we're turning our original problem, which is a high dimensional action space, into a low dimensional action space problem, and we're paying for it by increasing the size of the state space. Which, of course, that's something which we're better able to handle. So, okay. So I think that idea is hopefully somewhat clear. Is that idea clear? I think, yeah, basic idea. Okay. We're transforming the problem. We take an original MDP and we turn it into a new MDP, the so-called augmented MDP. Okay. So here's here's how it happens in our system. A lot more neural networks. So what we're going to do, if this is not clear already, is we are going to select each of the dimensions of SE3 sequentially. So first, we're going to make a decision about the XY location. So think about it like you're reasoning, your policy is reasoning about where it needs to move the arm next in order to like build that structure. So first, this system, this Q function is going to decide the XY coordinates it needs to move to. Then it's going to decide the theta it needs to move to, then the Z, and then these two out of plane orientations. So the way that's going to happen is that we're going to have the same fully convolutional network that we had before, this Q1, which is going to tell us the XY location, and then we're going to select that. Now, knowledge of the action that we took is going to be encoded in the form of an image patch, which is centered at the location of an image patch of the original image, which is centered on the location which was selected in the first stage. This fits into the augmented MDP formulation because we're allowed to use information about the action we just took. So it's like a projection of that information. So you get this thing. We're also being able to look at the original image. It all goes into this Q2 network, which makes a prediction about what theta to take. And then the process continues. We make a decision about what Z to move to, and then the out-of-plane directions that we want to take. Now, these are top-down images on the left, and there's some kind of three-dimensional type stuff on the right, which is not really super important. So bottom line, we're selecting the dimensions of SE3 of this SE3 action sequentially, and it's enabling us to learn policies in SE3 action spaces. So yeah, so now experiments. So I told you I was going to benchmark on block construction. So here we go. We have these three relatively simple block structures which we want to build. So the one on the left is just one block on top of the other. So I'm comparing against DDPG and the fully convolutional method I introduced at the beginning of idea number 2. Yeah, so for the very simplest of these problems, well, okay, so the thing that pops out, the main thing I want you to notice from this slide is that DDPG dramatically underperforms. It's like not even, so for, it underperforms here. And for these two, which are just slightly harder than the first one, it's like it doesn't learn anything at all. And these are averages over, a number of runs, not single runs. So in the first case, you notice that both the fully convolutional method and our approach is this thing, ASR SE3. That's the augmented state approach. So our method and the fully convolutional method, they both, basically perform equally well, and they basically get up to like 95% success rates. On this structure, where DDPG just fails, and our method slightly outperforms the fully convolutional method. And then over here on the right, we significantly outperform the fully convolutional method. But, things are not working great at this point because this is, about 60% success rate. So that's not good. But still, I mean, it's, the point is that we're using off-the-shelf DQN, the simplest of all the reinforcement learning algorithms, and we're performing reasonably well on these are not, I wouldn't say these are super complicated problems, but they're not like super trivial problems either. So for example, they're more complicated than things we saw in the OpenAI benchmark. So here we go. We're assembling, we're assembling this thing. So in this picture, you notice there are those two cardboard ramps on the side. So the whole point of having that in, this is some experiment to force the robot to reach to out-of-plane orientations. So the objects are kind of distributed randomly at the beginning of each of these trials. And of course, it needs to assemble the structure. So, okay. So far so good, I think. So the good, we've learned a policy in a 6-DOF action space. Even simple DQN seems to do something non-trivial. Downside, we saw a real drop-off in success rate when we got to the more complex structure, which is like just a stack of 4 blocks. So I'm going to try to address that next. That idea is basically an imitation learning approach. So I guess the way I see it fundamentally, there's only so much that a complete model-free method is going to be able to learn without bringing some kind of prior knowledge to bear. A convenient form of prior knowledge is the demonstrations. So that's what we're going to do here. We're going to do imitation learning, some form of imitation learning based on demonstrations.
Hey, Rob, quick question. Did you say sort of how you're representing the target configuration in this?
Yeah, okay, I'm not. Each of these block construction tasks is represented as a separate task so it learns a separate queue network for every different structure it wants to build, okay? So you're right, we want to be able to learn a policy that can assemble any structure. And we haven't done that yet. Right now, it's just learning a particular one.
But when you're scoring it, I mean, you even have to, just to be able to evaluate a potential action, don't you have to?
Okay, so when you're scoring it, so the learning happens in this pi bullet simulation, and we've engineered some kind of reward function that checks the structure to see whether it's a good one or not. So you would, for example, check to see whether there are 4 blocks balanced on top of one another.
Okay.
So we saw that the spatial action space looked like it was working, but DQN looked like it was underperforming. And we're going to try to solve that underperformance problem now. So the idea is that, so we're going to do imitation learning. So the idea is that human demonstration, in principle, you could use human demonstrations, so-called human expert demonstrations, but that takes a lot of effort because you have to find a human who's willing to do that. So in this case, we've got some kind of a planner that operates in the simulator, which produces successful trajectories. So this idea is based on, I think it's a pretty well-known now, there's an asymmetry in robotics between train time and test time. At train time, you generally have access to a simulator. You don't have to use it, but you have access to a simulator. The simulator has full state information. At test time, you obviously do not have full state information. You do not have access to the simulator, et cetera. But at training time, because we're training in simulation and we have full state information, we can use a planner to generate expert trajectories, expert goal achieving trajectories. And since we're dealing with block structures, that's actually super easy to do. You just create a structure and then you deconstruct it and generate and then reverse the actions, and it gives you some sequence of actions that results in a stable structure. Okay. So what we're doing here is a pretty standard imitation learning approach where there's some degree of on-policy experience, there's some degree of expert experience. It all gets kind of munged together in policy learning, and then it outputs a policy. So to be a little more specific, what we're doing is doing a variation on DQFD. So DQFD is, that's short for, this is a 2018 paper I think, is deep Q learning from demonstrations. So this is essentially an imitation learning approach. The way this works is that you're doing Q learning. So you use a TD loss, but there's this secondary large margin loss. Now, actually in DQFD, there's like 3 other loss terms, but those are kind of not super important to this right here. Key idea is that there's in addition to the TD loss, there's a secondary large margin loss. This large margin loss is, I'm not going to quite try to unpack this equation here, but it's penalizing non-expert actions. So as you go, so for every action in every action that we evaluate this loss function for, we're going to evaluate the loss function for some transition, and then we're going to we're going to back propagate the gradients. For every action that we do, we assume that we have access to an expert action produced by the planner. That and this large margin loss term is going to generate a penalty in the Q function, which is going to depress Q function values for non-expert actions. It's not going to totally it's not going to totally rule them out. It's just going to bias the system, bias the TD learning agent toward expert actions. And there's a little bit of complexity in terms of like some scheduling and whatnot, which I don't want to talk about here. So this is cool. DQFD is cool because it can outperform the expert. So standard behavior cloning, the best you can do is achieve expert performance. It just learns until it gets to expert performance, and then you're done. Now, DQFD can outperform because it has this TD loss term. So it can like make slight modifications to the expert to try to do better. We have, in order to, there's challenges. So doing acting in a spatial action space is the standard algorithms don't work very well because the action space is so large and complex. And in this case, we modify the large margin term essentially to account for the fact that there could be multiple good actions instead of a single one. So this term looks similar to the large margin term, but it's able to apply to a bunch of actions rather than a single one. So this idea, simple enough though it is, enables us to just dramatically, from a practical perspective, we do dramatically better than DQN. So here we're learning to build the structure that you see there in the picture. DQN never gets, it's not getting above basically 65% success rate. And our method is getting into the low 90s. We're outperforming DQFD, where we outperform all imitation methods that we know of being relevant here, which is primarily something called ADET and DQFD. Okay. So one of the cool things about model-free types approaches like this is that they generalize pretty well to like different kinds of objects. So, I think people often think block structures is really easy because perception of blocks is just easy. But the point is that the reason it's valuable to do this kind of stuff is that to use model-free methods, that we can change up the distribution from which the objects were sampled, and the method works basically as well. Not quite as well, now we're in the low 80% success rate rather than 90%, but we're drawing objects from basically some kind of like arbitrary set of, we have some sampling mechanism for sampling objects, sampling arbitrary objects. We train the system on those arbitrary objects, and then we can basically run it on any sort of objects we happen to come across in the real world. So what this real world policy is trying to do now is it's trying to build the requisite structure using whatever block components are available to it. And it's going to use those components in a way dictated by whatever shape they seem to be most similar to. Okay. All right. So this approach translates. So one of the things, all this training happened in simulation. One of the, I think, somewhat important things to see here is that we didn't, since we're using purely depth images, we're not using any RGB images. The problem of domain transfer is a major problem when you are dealing with RGB images, because it's really hard to simulate RGB images, which are similar to what you encounter in the real world. Not so with depth images. So depth images, pretty easy to simulate. You just need a bearing from your sensor location. And they generally, we seem to be able to apply the policies learned in simulation directly to the real world without a whole lot of problems. Now, in other work, we definitely observed that there's, you can improve things by doing some kind of domain transfer. But the point is that the problem is not so huge that doing nothing is not an option. So we run this stuff, run policies learned to create some of these various structures on a robot, and we get what I think are pretty strong results. We can stack these things with 80, 90% success rate, 80% success rate. Like I said, these are somewhat challenging things to assemble because if the objects aren't balanced all right, the structure's going to fall over. So at this point, what do we got? We have a mechanism for learning policies to solve a single block construction task. So one of the things which we're looking at, as I guess Josh was alluding to, is transfer to other tasks, learning to solve a set of tasks kind of jointly, so the multitask setting or like a meta reinforcement learning setting. So one of the things we've looked at is something that's, I hesitate to call it meta reinforcement learning approach, but it's a method that's approaching basically that problem. So the problem we're trying to solve is this. Your robot has already solved 19 different block stacking tasks. And now it wants to extract some sort of useful information from those 19 solutions that is going to somehow enable it to more quickly solve the 20th task. And the 20th task, it could be anything. So this is, you're still going to have to do some learning on the 20th task, but you're hoping to speed that up. Yeah, how do we leverage prior policy knowledge in order to solve the tasks? So the take we're taking, the approach we're taking here is to leverage something known as action priors. The action prior idea is extremely simple. You get policies for the first 19 tasks that you've solved. And maybe it's not 19, maybe it's like 2 tasks that you've solved. It's, the principle still applies. You get these policies for the first 19 tasks you've solved, and you distill those policies into some like meta policy. So the meta policy essentially represents a max over, a normalized max over all of these constituent policies. So if you were to follow this action prior policy, the behavior you would take would be to take actions that would build one of these structures with equal probability. And maybe it would create none of those structures. First, it would take an action that would solve structure 1, and then it'd take an action that solves structure 15 or something. But it's only taking actions that have been seen to be useful in the construction of one of those structures in the past. Okay, so that's the action prior policy. What we're going to do is real simple. We're going to do Q learning, or I'm sorry, we're going to do DQN. We're going to do DQN, and some of our experiences are going to be on policy. You have to do stuff on policy in order to do any sort of policy learning. Otherwise, either that or you have to account for the fact that you're off policy, and that's not easy. We're going to do some on policy experience, and then instead of just generating random exploration, we're going to generate exploration from the action prior policy. So when we explore, in order, and this is in an effort to solve problem 20. So we've solved 19 tasks. We have distilled those 19 policies into the action prior policy. Now we're trying to solve task 20. And when we do exploration for task 20, we are going to, instead of sampling actions at random, we're going to only sample actions that were useful in one of the tasks that we've seen before. And this is a particularly, I think this is a particularly intuitive approach, especially for this type of problem, especially for manipulation problems. You know, you think there's a large action space, there's, or to say equivalent, there's all these different places where you can move a hand. Now this action prior policy is going to only explore locations of moving the hand that basically are going to pick up some block, or do some placement in a way that has been stable in the past. So this action prior policy is basically only going to sample grasps, and it's only going to sample stable placements or structurally relevant placement behaviors. And this method works pretty well. So this is on a benchmarking problem, but this, basically, like we outperform all of the benchmarks which would be relevant here. So this is, I describe as a meta learning problem, but you can't solve this problem using something like MAML, for example, because the networks, the neural networks that encode the Q functions in our problem are huge. It's like a ResNet. We have a UNet. You can't do MAML with a UNet because MAML is a meta loss function, and inside of the loss function, you need to calculate the derivative of the UNet, which so that only works for smaller networks. Because this method is simple, it can be very effective, and it outperforms progressive networks or some weight sharing strategies. Now this is just on a simple benchmark domain, reinforcement learning-ish domain. On our construction problems, it basically enables us to learn to solve new construction problems without needing the expert demonstration. So the point here is that, I guess the meta point to be taken away from all this is that if you want to learn interesting policies, learning policy learning, you need some kind of prior. That prior can come in the form of expert demonstrations, maybe generated by a human, maybe generated by a planner. It can also come in the form of some sort of prior derived from previous tasks that you've learned. So that is basically the conclusion of my talk. I want to end with something slightly different than block structures, for fear that you think that I'm only interested in solving block structures. So I think that the problem that motivates me, I think, is solving domestic manipulation tasks. So do the dishes, make coffee, do the laundry, etc. Josh, I talked to Josh before. He told me they've been waiting a long time for the coffee making robot. I'm hoping that that we'll get there soon. This is definitely one of the tasks that motivate. So I just want to be clear. The kind of problems we want to solve are these problems in unstructured environments. So for example, with coffee, you're making coffee. The robot knows it's making coffee. It doesn't know, it knows that there's going to be a mug involved, a coffee maker involved, that it has to find the coffee maker. Sorry, it has to find the mug. It has to maybe place some coffee grounds into the coffee maker. It knows all these very general things that you know when you make coffee, but it doesn't know the geometry of the mugs. It doesn't know where the mugs are located. Maybe it hasn't operated this particular Khoury before, so it doesn't know exactly where the on button is located. Okay, so this is, you might think of it as an open world task where you know the task at the high level, but the robot needs to kind of figure out how to actually do it itself. Yeah, obviously a very important problem if we ever hope to send robots into the home to do useful stuff without a whole bunch of learning on the fly. So this is what we want. we haven't gotten there yet. One thing which we have been doing is looking at extending the work that I've spoken of here to some real world settings. So this simulator is not nearly as sophisticated. So this is pi bullet simulation, not nearly as sophisticated, I think, as what you're used to. But it still adequately simulates physics, I guess, for our purposes, at least to convince us that the robot would be capable of picking something up when something actually gets picked up. So in this problem, there's a couple of drawers. There's a teapot and a lid. Somewhere in the drawers, you don't know exactly where the teapot and the lid are. You need to remove the teapot and the lid from the drawers and put the lid on the teapot. So the teapot, there's obviously, there's geometric variation over the space of teapots that you might happen to see. There's different drawer geometries that the robot might be exposed to. And I'm somewhat heartened. You know, there's some additional stuff that has to happen here to make this, you know, generalizations of the ideas I've talked about, but nothing fundamentally different. Now we're programming a robot to perform this particular task, but it seems to work real well. So what the policy that this thing learns is doing the following. It's opening a drawer. It's not sure what it's going to find in the drawer, but you know, it removes stuff from the drawer and it puts the lid on the teapot. So if it picks out the lid first, it has to put it down and then get the teapot and then put the lid on the teapot. If it gets the teapot first, it can put that down, then it can just directly put the lid on top of the teapot. Now it has to reason about what order in which to open the drawers. It always opens the bottom drawer first, because if it opens the top drawer, then it has to close the top drawer in order to get stuff out of the bottom drawer. And that is, as you can see, not an optimal solution. So it avoids that. So that's it.
Yeah, thank you so much. Do people have questions?
So I was wondering, like two questions. One is on goal specification. So what are your thoughts on like the best way to specify goals? The other question is on action priors. I was wondering how do we decide the number of tasks that are required to get the optimal action priors?
Okay, goal specification first. Yeah, so I think, so in these block stacking tasks, you could probably specify goals using, you could imagine some sort of symbolic-like representation where you would specify the contents of the various layers of the structure. You'd want something that enables you to specify novel structures so that you're not condemned to always producing structures you've seen before. To answer the general question of goal specification, I mean, the thing that pops into my mind is like a PDDL, a PIDL specification. I mean, I think symbolic representations make a lot of sense here. Now, the symbols are going to have to correspond to classes of objects, not object instances. But for many of these tasks, I think it's reasonable to think that there's certain classes of objects you expect to see. So goal specification for coffee might be, you know, cup and pot and, you know, grounds and maker and so on.
And I think there was a question regarding these action priors, right? I think.
What was the action prior question?
So how do we decide the number of tasks that are required to actually?
Ideally, you use all of them. That sounds like an attractive. I hate having to choose. If I had to choose, I'd probably have to learn something. I would have to learn something that could do the choosing for me. It's not clear that I do have to choose though. I mean, so the idea is that your agent is just successively learning more and more tasks, and it's just learning the tasks in the order in which it has to learn the tasks. And for whatever tasks it's learned, that supplies information that it's going to be able to use in the future.
Yeah, thanks.
Yeah, I mean, it's not like you say, well, I want to solve this 20th task, so I'll carefully choose out the 19 tasks that I have to solve before that.
I have a question regarding these augmented state or actual representations then, or the state representations.
Yeah.
Is that, so intuitively, it makes sense to say, okay, you first have XY because that's kind of focusing on the image space, right? And then you have orientations conditioned kind of on that. And I guess there are some connections to other these autoregressive models that rather than sampling from a high dimensional joint distributions, you do it one variable at a time conditioned on previous ones. Do you feel like, or how important is, for example, the ordering in which you do that with these? And do you feel like there's always a straightforward way for kind of constructing this sequence of sub-actions?
Yeah, that's a great question. Not clear. So in our work, this doesn't, this stuff doesn't seem to be particularly sensitive to that. Now, the first selection is the XY because the fully convolutional network is somewhat special in that it hardwires a form of equivariance that is useful to us. So that's kind of needs to be tied to that first network. The rest of the variables, I mean, certainly we reasoned about it and we did the thing. We used the ordering, which seemed to work best. So this augmented state representation, it hasn't been used very much at all. Recently, the other setting which has been used is kind of like an OpenAI Gen setting where like you're trying to control a humanoid and there's 19 dimensions that have to be controlled and you select them one at a time. And I don't think that there's, I don't think that those folks had a really good answer in that work.
Rob,
I don't know.
Seems like for rotation and translation of blocks, like those two operations commute with each other. So it would be natural that the order might not matter. I wonder if you had two operations where like they didn't commute, maybe the order would become more important.
Yeah, right. That sounds fair. I mean, there's these networks are also, if you remember back to my that slide, we were hand coding the input into the network to be a patch that was kind of focused on the previous, based on the distinctions, the choices that have been made previously. So, yeah, I mean, I like in SE3, I don't think it makes a whole lot of difference. Although the other thing I should say is that this, the top-down representation and, like the Euler angles or the out-of-plane angles, like it's a little weird. Like it doesn't work for large out-of-plane orientations. So it's probably not, it's not fully an SE3. It gives you a little bit of SE3. In order to handle like gross SE3, we have to have like different networks looking at the world from different angles. I don't know. I just don't have good answers.
One more question maybe is also, I like the idea with these action priors, right? Where the notion is somehow, how can we reuse this previous experience in general, right? And then do faster training of new tasks or complex tasks. There's one line of work that's also pushing towards maybe learning kind of representations, right? That are just very useful for many follow-up tasks. In computer vision, of course, they've been very successful with using contrastive learning for learning kind of image representations that can then be fine-tuned on many different image classification tasks and things like that. It seems like in robotics, we're still having trouble doing that.
Yep.
And what are your thoughts?
Yeah, so well, this is like one of the grand challenges in AI is to automatically find task or domain appropriate abstractions. So, I mean, yeah, we've been working on it. And I would say like, we don't have super good answers. The direction that, I mean, there's a lot of different directions so that you can approach problems. So, I mean, from a high level, I view like what we're talking about is hierarchy here, abstraction. I think it's clear that in order to solve end-to-end problems, you need abstraction. And I think like the success of task and motion planning is kind of an example of that. Even in a planning world, you want to plan at multiple levels. How does that work in policy learning framework? I mean, my thought is that if we do figure out how to find, either learn or program the right abstractions of a policy learning framework, it's going to dramatically increase the power of these policy learning methods. What we're doing in this case, obviously, is we hand coded this action abstraction, using collision-free motion planning, which seems like a reasonable thing to do. So we've done some work trying to learn abstractions using MDP state and action abstraction. So there's something called a MDP bisimulation, which it clusters states based on behavior. So similarly behaving states get combined in a similar way. I know that this idea, Ollie Brock had done some work in the late 2000s, kind of along these lines as well. He was just kind of like a robotics inspired type approach, but those things have very strong theoretical footings in reinforcement learning and MDP theory. There's also something called MDP homomorphisms, which I'm really excited about. It provides, a great theoretical framework for action abstraction. We spent a bunch of time working on variational approaches to finding abstractions, and it's just hard to do. Contrastive learning is great. It works well. Fundamentally, it's contrastive learning is pushing apart. It's a rule for pushing apart some pieces of data in your latent representation. It doesn't really solve the problem, but it gives you a knob to tune. So I guess the short answer is, I think abstraction is great. I wish I knew how to do it.
Yeah, I agree. I think that's also, we're kind of out of time. So that's a good ending to a great talk. Thanks so much. And see everybody.
Yeah, thanks everyone.